Hi folks, welcome to this presentation on a list of GDC techniques for Paper 2 for the IB Math AASL course. There are often many different ways to accomplish tasks, but in this video I hope to go over some things that will get you through the exams at the very least. I'm going to be working with a TI-84 emulator with OS 2.55. So in your GDC, one of the most important things to be able to deal with is graphs. You need to be able to enter functions and choose appropriate window settings. Zoom 6 gives you a standard grid. So let's put in these two functions. I turn my GDC on, I go to y equals, and I enter them in. Now that they're in there, I'll press Zoom, and then 6 for a standard grid. And it generates that parabola and that line just as I expected. Now that I have those functions in there, I want to be able to deal with the calc menu, which is second trace. And there are 7 important functions in there. The first is value. So let's suppose I wanted to know what f of 4 is. Of course, I could put it in there and work it through, or I could head to my GDC, and I'm going to press second trace to get to this calc menu, and I'll choose 1 for value, and then I'll just tell it the x value is 4, and hit equals. And it will tell me on that parabola, which is my y1, or the f of x, when x is 4, y is negative 3. If instead I had wanted to say g of 3, well, again, it would be easy to sub it in, but I could also just tell it I'm looking for an x value of 3. I hit 3, enter. Now here it's still on my y1, or my f of x function, but if I tap down, then it will go to my next function. It will tell me when x is 3, y is 2. I can also find important information about values by going to the table. So if I press second and graph, it shows me the x and y values for both of those functions. So I could just go down and see when x is 4. Oh yeah, the f function, or y1, is negative 3. When x is 3, the y2, or g function, is 2. So that can be helpful as well. Our next important feature is looking at zeros. So these are x-intercepts on the graph. So let's suppose we want the x-intercepts of f of x. I could head to my calculator. I'm actually going to turn off the second graph, so I can just go over to the equal sign and hit enter. And now it will only graph that first one, that parabola. If I want the zeros, I press second and then trace to get to this important menu, and I choose 0. And it's going to ask me some questions. It's going to ask me about the left bound. So I need to go a little to the left of the first x-intercept. Then it will say right bound, question mark. And I go a little to the right of the x-intercept, hit enter. And then guess. I go right on that x-intercept, or as close as I can. And it's really important here that I hit enter again. If I don't, then it won't calculate anything. And it tells me that there's a 0, or an x-intercept, at x equals 1.42. But wait, there's another x-intercept. So to find that, I'll do the same thing. I'll go to my graph and I'll press second trace to get to this calc menu. I'll choose 0. And I'll go a little bit to the left of that second x-intercept, hit enter. A little bit to the right, hit enter. Go right on it and hit enter one last time. And it will tell me that there's another x-intercept at 4.58. The next most important feature is probably the max and min features. So if I have a parabola like I do in f, I might be interested in where its minimum is, what its vertex is. So to do that, I can go and take a look at the graph again. I press second, calc, and I find this nice menu again. I'm going to choose minimum here because this parabola has a minimum on it. And I go a little bit to the left of the minimum, and then I go a little bit to the right of the minimum. And I'm hitting enter after each one of these. And then I go and guess where I think the minimum is and hit enter one last time. And it's going to tell me that the minimum occurs at 3, negative 5. The actual minimum value is the y value, the negative 5, and it occurs at an x value of 3. Probably the most important feature on this graphing stuff is the intersect feature. So if I'm wondering where f and g intersect using those definitions from the last slide, I can go and turn my G function back on, so I'm going to see them both. I'll hit graph. And we can see that they're going to intersect in two different places. And to find the coordinates of those intersections, I press second trace to get to that same menu. I go down and I choose intersect. And this time I have to go, and it's going to ask me a couple of questions. It says, is the first curve that one that's up top, the y1? And I hit enter to say yes. And then it says, is the second curve that one up top that says y2? And yes, it is. There are only two curves, so it must work well here. And then it will ask me to guess where that intersection is. So I'm pretty close here to one of the intersections. I'm going to hit enter. And it tells me right away the intersection's at 1.36, 0.363. Now you can tell that there's another intersection, so we just go through the same process. Second, trace. I'm going to go down and choose intersect. And one of my students has this way of doing this that works very well for her. She will just go ahead and get close to the point of intersection and then mash enter a few times. So there's the point of intersection, and I'll just hit enter 3 times. First curve, second curve, guess. And there's my point of intersection, 5.14, 4.14. The reason that the intersect function is so important is that it allows us to solve pretty much any single variable equation. And to do that, all we need to do is graph the left side and graph the right side and see at what x values they intersect. So I'll just put in those functions, in for y3 and y4. I turned off the other ones. I'm going to graph. And I've got an exponential function and a line. I actually know that there are 2 points of intersection there. There's one that's around -3-ish, and there's one I can see more clearly at around 1. So I'm going second, trace. I'm going to choose intersect. And here's my first curve, second curve, and I'll guess. Okay, and I get -2.92. While I'm at it, I might as well find the other point of intersection. So second, trace, I choose intersect, and I'm going to have to go over a little closer to that other point of intersection. First curve, second curve, guess, and it tells me that there's an answer at 0.974. It is very likely that you're going to run into equations that you can't solve analytically, so having this technique really helps us out. The other 2 features under that calc menu have to do with calculus. So if I wanted to find f prime at 2, I just have to use this dy by dx function. I'm going to turn off the functions that I just had, and I'll turn back on my y1, which was f of x. So if you recall, this was a parabola. If I want to find its slope when x is 2, or its gradient when x is 2, I go second, calc, I go down and I choose this dy by dx, and then I just have to type in 2 to tell it I want the slope when x is 2, and it will tell me that it's -4. Similarly, if I want the definite integral over some interval, I can go to the same menu, so that's second, trace, go down and choose the definite integral, or the integral sign down here, hit enter or just hit 7, and it will ask me lower limit, so in this case that was 1. The upper limit is 5, and I'm just reading that from the integral itself, and it tells me the answer is -9.33. So again, I read those limits for it from here, the 1 and the 5. That gets us through a whole bunch of graphical stuff. The next selection of features we'll take a quick look at is what you'd find by hitting alpha and then the top row of buttons. Most of these can also be found under math, but they're a nice shortcut this way. So if I hit alpha y equals, I get this little menu. And the n over d is really nice. So here I can put in something like 3x minus 2 all over x plus 1. I can just put in something that looks like it's sort of textbook formatted. Another thing that's pretty helpful is this sigma notation. So if I press alpha and then I hit window, there's a sigma under number 2. If I wanted to evaluate that summation, I could just say, in the question it says p equals 1, I'm going to have to say x equals 1. So from 1 to 20, of 2x minus 3, and just hit enter. And it works it out for me. Pretty slick. The n-deriv does the same thing that we could do with the graph, but you don't have to put in the graph. So if I wanted to find this f prime of 2, which we already found right back here, I could do it like this. Alpha, and then window, and there's this n-deriv, that's number 3. And it'll say the derivative with respect to x, and then I'll tell it about f of x. Now another neat thing is that instead of writing in f of x again, I can hit alpha and then trace, and it gives me all of my y variables. So I've already defined f of x as my y1, so I'll just choose it there, and it will put it in. And lastly, I'll tell it at x equals 2. Let's see if this gives us the same answers we had before. Yep, we get -4. And it does say there your y1 function can be accessed through alpha trace. It saves you a whole bunch of recopying of functions when you're doing your exam, so it can save you time. If you want to find a definite integral without actually looking at the graph, you can find similar stuff here. We can go alpha, window, and we'll get fn int, that's number 4. And this is also under the math button. And you can just put in a definite integral the way that you see it, from 0 to 3 of x minus 1 dx. You can also find log base, so that's under alpha, window, same as the last few. We go down and choose log base. So if I wanted to find the decimal approximation of the log base 2 of 7, I can just type it in and I'll get 2.81-ish. Now we should not really need this because we have the change of base rule that would say you could just do ln 7 over ln 2, or you could do log base 10 of 7 over log 2, but it's nice to have. The last little piece here that might come in handy is absolute value, especially when you're talking about area between curves and distance traveled. So let's say I wanted the same kind of integral as before, but with some absolute value signs. So the absolute value of x minus 1. I can go alpha, window, I'll get that definite integral by pressing 4, and I'll tell it from 0 to 3. And now I'm going to go ahead and say alpha, window, and get those absolute value brackets. That's the first one, ABS. And I can type in x minus 1 dx. Often this is a little more computationally heavy on the calculator, and it has to think for a second, but it's going to give me 2.50. Or in this case, it would be exactly 2.5. That takes care of the algebraic and graphical stuff, so let's move on to statistics. We're talking about basic descriptive stats here. So you need to be able to use your GDC to quickly find mean, median, standard deviation, and quartiles. And there are kind of two scenarios. You could just be given raw data, so just a bunch of numbers. And if that's the case, then just enter that data into list 1. To do that, I press the Stat button. I press Enter to edit a list. And then I just enter my data, 7, 8.5, and so on. Once all my data is in, I'm going to press second mode. This is a really important feature because it quits. It gets you out of there. And now I'm going to press Stat again, and I press Over and choose one variable stats. So that's what we're talking about right here, stat, over, and 1. One variable stats. And the list that I'm talking about is list 1. I have no frequency list because this is simply a collection of raw data. And I hit calculate, and it will tell me the mean. The mean here is 7.8125. And I can go down and I can see standard deviation, that's 1.30. We're always going to be using the population parameters in MathSL. And I can also go down and look at the minimum, the Q1, the median, the Q3 values, the number of pieces of data, and so on. Alternately, we might be given a frequency table or graph. So things are going to be very similar. I'm going to press Stat to get into those lists. I need to get rid of all my data. So I go to the very top, and I press Clear Enter in the list heading. And in the first list, I'm going to put in the actual data values, 4, 5, 6, and 7. And in the second list, I'm going to put in the frequencies, 3, 6, 4, and 3. Once again, I'm going to quit. So second mode, and then I go Stat, I go over, and once again, I'll choose one variable, statistics. This time, though, there is a frequency list, so I've got to tell it where to look. It looks for my x values in list 1. It looks for my frequencies in L2, which is just second 2. And now we can calculate. And it'll tell us about the mean, it'll tell us about standard deviation, and so on. Now that we've done some basic descriptive stats, let's move on to probability distributions. We'll probably be working a fair bit with the normal distribution. And these features are found under the Distr menu, which is second vars. And the two features that we're going to use are normal CDF and inverse norm. If a question has z-scores or standard scores, that means that the mean is 0 and the standard deviation is 1. And the GDC is going to require you to enter an upper and a lower bound. So we'll do this in the context of an example. Suppose the head circumferences of newborn babies are normally distributed with a mean of 33 centimeters and a standard deviation of 1.5 centimeters. Find the probability that a randomly selected newborn has a head circumference between 31 and 34 centimeters. Okay, so let's think about this. 34 would be a little bit above the mean. 31 would be a little bit below. We're wondering about this area. In other words, we want the probability that the head circumference is between 31 and 34. Now, for normal distributions, don't worry about whether you have an equals on those less than or greater thans. Being actually at a value, because it's continuous data, doesn't really matter that much. What does matter here is whether we're going to use normal CDF or inverse norm. Normal CDF is for finding an area or probability. Inverse norm, on the other hand, is for finding a score. So in the situation we've outlined below, we're looking for a probability. This is going to be a job for normal CDF. Now, you can also do this with the shade norm function, but personally, I don't really want to be messing around with window settings. So I'm going to go second vars, and I use normal CDF. And it's going to ask me, what's the lower bound? Well, it's 31 for us. What's the upper bound? It's 34. What is the mean? It's 33. And what is the standard deviation? It's 1.5. And now I just paste and hit enter. And it works it all out for me. 0.656. The next question asks, well, what's the probability that it's greater than 35 centimeters? So I think it's really important in these ones to draw a little picture. We're again looking for an area. So what is the probability that that head circumference is bigger than 35? I'm going to go through the same process. Second, vars for distribution. Normal CDF. This time the lower bound is 35. And the upper bound actually doesn't have a boundary. So what I'm going to do is just tell it it's really, really big. Now, of course, there's no newborn head with circumference of a bajillion centimeters. But we want it to just keep increasing without bound. And the mean stays the same, and standard deviation stays the same. And we just hit equals. And we get 0.0912. In the last one, it's asking us what's the probability that it's less than 31 centimeters. So here's 31. I want to find this area. It's going to be a similar setup. Once again, we need to go second, vars, choose normal CDF. Here, the lower boundary is negative infinity. Now, again, there are no head circumferences that are less than 0. But anytime it goes all the way to the left, I'm just going to put in negative a whole bunch. Okay. If you put in 0, it'll probably still work out the same to 3 sig figs. The upper boundary here is 31. Everything else is the same. And we get 0.0912. And that's because both of these values, 35 and 31, are an equal distance from the mean. So there's some symmetry going on. But you can just plug it into your calculator and chug. We've found a bunch of probabilities or areas at this point. Now let's do some of these inverse lookups. So this is where you're looking for a score. You're trying to find the score. And you need to tell the calculator the area that's to its left. So here's an example. The lengths of songs on the Billboard Top 100 chart for the past 10 years have a mean length of 230 seconds and a standard deviation of 23 seconds. So here's what's going on. 230 is the mean length. 98% of songs have a length less than A or shorter than A. So here's 98% of the songs. Find the value of A. This is a case where we want the score, so we use inverse norm. I think of inverse norm as a normal distribution superhero. So I'm going to go second, vars. I'm going to choose, this time, inverse norm. I'm going to tell it I'm talking about an area of 98%, so that would be 0.98. The mean here is 230. The standard deviation is 23. And I just hit enter. And it tells me that A is going to be 277 seconds. These questions used to be a lot rougher, and we'd have to use z-scores for almost everything. But now the calculator interface is quite nice, so you can just use this little wizard and it finds that value for you. That doesn't mean, though, that you never need z-scores. Just to recap, a z-score tells you how many standard deviations you are from the mean. A positive z-score means above the mean, a negative z-score means below. There's a little formula that lets you compute z, and it's this. Z equals x minus mu all over the standard deviation, where x is a raw score and z is the standard score. So we've got an example. The weight in pounds of Yorkshire Terriers, or Yorkies, is distributed according to this distribution. So mu, or the mean, is unknown. This is telling us the variance. It's also telling us that standard deviation is just going to be 0.7. Yorkies that weigh 7 pounds or more are called giant Yorkies. For real. Suppose 15% of Yorkies are giant Yorkies. Let's draw this. There's some mean that we don't know, and we're going to look for. There's some weight up here of 7, and 15% of Yorkies weigh more than that. And we also know the standard deviation. It's very difficult for the calculator to find mu directly for us. What it can do instead is find the corresponding z-score. Okay? And so if you're looking for a z-score, you're talking about a situation where the mean is 0 and standard deviation is 1. Let's head to the calculator and find the z-score. We'll go second vars. This will still be inverse norm. And the area in this case will be 0.85. That's because since there's 15% to the right of 7, there's 85% to the left of it. If we're looking for a z-score, the mean is 0 and the standard deviation is 1. I work this out and I get 1.0364. I'm going to keep a bunch of sig figs at this point, and I'm going to round at the end. So now I have a bunch of information. Z, that we're talking about for these giant Yorkies, they're a little more than 1 standard deviation above the mean. X, that would be our actual weight here of a giant Yorkie, or the cutoff for the weight of a giant Yorkie. Mu is unknown, and sigma is 0.7. I'm going to have to multiply both sides by 0.7. So I'm going to keep all those decimal places in my calculator and just go times 0.7. and I get this 0.7255. And I'm going to move the mu to the left. I'm going to subtract 0.7255 from 7. So I'll go 7 minus that answer that I just found, and get 6.27. These two examples on this slide both use the same basic technique in the calculator. It's just one was a little more involved than the other. The other probability distribution that we're likely to run into is the binomial probability distribution. And before we get into that, let's look at binomial expansion a little bit. So if I were to expand this expression here, I could write it out this way. Now, if you want to go through how that all works, you can check out the algebra review video. But the main thing here is that there are going to be combinations that need to be evaluated, like something like 5C2. And the easiest place we can find that on the calculator is by typing in 5, then we hit math, then we go over to PRB. And that's where you'll find NCR. So 5C2. And we can work out that 5C2 is 10. We could also have found it by Pascal's triangle, or we could find it using the formula for NCR, which is n factorial all over r factorial n minus r factorial. So for 5C2, we would say it's 5 factorial all over r factorial, so that r would be 2, so 2 factorial, and then n minus r, so 5 minus 2 factorial. You could write this in your calculator using the nice numerator over denominator, 5, and to find factorial, we press math over for PRB, and there's the factorial button. And I can do the same thing for 2 factorial and 3 factorial. Bit of a waste of time, though, because we could do it more efficiently using just the NCR button. The other thing we can do is look at this analytically. So that's 5 times 4 times 3 the rest of the way down, all over 2 factorial, 3 factorial. 3 factorials divide out. So we really have just 20 over 2 factorial, or 20 over 2 makes 10. So a bunch of ways to do it, but really what you want to be able to do is use that NCR button on your calculator. Now that brings us up to binomial probability distributions. And these features are binom PDF and binom CDF. And they're found under distribution A and B. Don't use normal PDF. Binom PDF shows the probability of exactly a certain number of successes, whereas binom CDF tells us about the probability of up to r successes, or probability that x is less than or equal to r. So let's look at that in the context of a problem. Studies show that 63% of teenagers eat breakfast regularly. Suppose a random sample of 5 teenagers is taken. So this is really a binomial distribution. We always say n, so we've got 5 people here, and p. And p. What's the probability that exactly 4 eat breakfast regularly? So when it says exactly, this is a binom PDF situation on the TI-84. The IB does not want to see your calculator notation, though. You can just answer with the numbers, or you can say px equals 4 if you want to show some notation. Here's how we do it. We're going to go second vars for the distribution. We have to go almost all the way to the bottom. Binom PDF. And it'll ask us the number of trials. There are 5, or there are 5 teenagers involved here. P, or the probability of success for any given teenager, is 0.63, according to the way we set this up. And X value is the number of successes. So we're going to say it's 4, and it will just run it through for us. We'll get 0.291. Now this next question is asking us for a whole bunch of other ones, and I just want to show you how you could get lists to deal with this. So we can press Stat, go into our lists and clear them out. And one thing I can do is think about the number of teenagers that might have breakfast regularly. So it could be 0, 1, all the way up to 5. Next, I can go to the L2 heading, and I press second vars, and I'm going to choose Binomial PDF, and I'm going to tell it that there are 5 trials and that the p is 0.63. This time I'm going to leave the x value blank. If you do this, it will generate the entire distribution for you. So I hit enter and enter again. There we go. We can see px equals 4 is right down here, but I can also read off some other ones. So the probability that x equals 0 is 0.00693. The probability that x equals 2, well, I can just read that off. It's 0.201. And the probability that x equals 3 is 0.342. I don't think doing the list saves you much, if any, time, but it's something that you can do. The next question asks us, what's the probability that at most 3 eat breakfast regularly? So, I mean, you could add up the probability that 0 do, and 1 do, and 2 do, and 3 do. But what's going to be easier is to do something like this. Find the probability that 3 or fewer do. And that is the job of Binomial CDF. So let's head to the calculator. This time we're going to go second, vars, and choose Binomial CDF, which is close to the bottom. Maybe the very bottom one. And we're going to tell it the number of trials is still 5. The probability of success is still 0.63. And in this case, we're talking about 3 as our number of successes. We hit enter, and that's going to give us 0.609. Lastly, we want to find the probability that at least 2 eat breakfast regularly. So here, this is the probability that 2 or more do. And you've got a bunch of ways that you can figure this out. You can add up a bunch of individual probabilities. But one of the simplest ways to do it is to think of it as the complement of 1 or fewer. Right? Because these are discrete numbers of successes you can have, there's just either 1 success or 2 success or 3 successes. So your calculator won't do these greater than ones, but it will do the less thans. So here we could go 1 minus, and we'll go second, vars, and go Binomial CDF. And this time we'll tell it that it's up to 1 success. Trials is 5, p is 0.63, and we'll work out to 0.934. Now, of course, there are other ways that you can do this. I'm just showing you one way that you can approach it with Binomial CDF. Last piece of the puzzle, regression and correlation. So correlation is found by using linear regression. These are really the same thing, or it's in the same place in the calculator. Make sure that stat diagnostics are turned on. So to double check that, here's what you do. I'm going to quit. I'm going to go second catalog, which is second 0, and I just go down until I hit diagnostic on. There's diagnostic off. Here's diagnostic on. Enter, enter. Hopefully yours has it on its default, but there it is if you need it. So we've got an example here where we consider the data where X is outside temperature in degrees Celsius and Y is number of tubs of ice cream sold at a store. Maybe there's a relationship between those two things. Let's put this data in our lists. So we're going to hit Stat, Edit, get rid of everything that's in our lists already, or just choose New List to work with and put in the data. Typically, we want to put X in L1 and Y in L2. Now I'm going to press second mode to quit. I'm going to find the correlation coefficient. So here's how we do it. We press Stat, over for Calc, and then down for linear regression. We press Enter, and we tell it that the X list is L1. That makes sense. The Y list is L2. The frequency list, oh, let's clear that. There is no frequency list. If you wanted to store the regression equation somewhere, like into Y1, you could hit alpha trace, and that will give you all those options. Maybe I'll put mine in Y5, just in case you want to see the graph. Most of the time, we don't necessarily need to see it, though. So the correlation coefficient is 0.961. We can find the equation of the y on x regression. This is the standard regression. And that's actually what it's giving us right here. It's telling us that it's y equals 3.32x plus 8.87 because it's telling us the a and b values. The y on x regression is good for using x to predict y values. On the other hand, if you want to predict x values, you need to do an x on y regression. And I think the simplest way to do that is to just trick your calculator. We're going to go through the same steps. I'm going to press Stat. I'm going to go over, and I'm going to tell it to do linear regression again. But this time, I'm going to tell it that my, quote, x list is L2. Now, I'll know that it still really represents the y variable. But I'm going to go L2 and L1. I've switched them around. And there's no frequency list. I don't even want to store it anywhere. I'll just calculate. Now, it's telling me here that it's y equals 0.279x minus 1.24. But I actually know that I switched in calc. So the equation of the regression is actually x equals 0.279, y plus negative 1.24, or minus 1.24. So we just trick our calculator. We switch x and y, or list 1 and list 2, and then we switch x and y in the actual regression equation to get an x on y regression. A y on x regression is more common, but you might see either one. Lastly, at what point will the regressions intersect? The answer to that is always x bar, y bar. So we can find the mean of the x values by adding them all up and dividing by 5, and the mean of the y's by adding them all up and dividing by 5, or we can use some of the tricks that we already learned with raw data. I'll leave that to you to do, but the result should be 16.2 is the average of the x's, and 62.6 is the average of the y's. Once again, this recap does not cover everything that your calculator could possibly do. I've left out the numerical solver in here because I prefer graphical methods, but there's lots of other stuff that you could conceivably use. I think this is enough to get you by, though, in the Math AA/SL exam. I hope this has been helpful. Good luck with the material, folks, and take care.